That's it. Hi. This is Julian. We are presenting the NEARCoder today, a Web3 code LLM that we built by fine-tuning SOTA 2 on the NEAR protocol. We will start by an introduction, presenting the datasets, and then the training steps and an evaluation. So just to start, to give you a bit of background, NEAR started in 2017 as an AI project by Ilya Polosukin, who's the co-author of this famous AI paper, Attention is All You Need. And in 2017, NEAR AI aimed to teach machines how to code before facing the challenges to pay worldwide contributors. So in 2018, they created the NEAR protocol, which is a payment network on the blockchain, and starting to promote self-sovereignty of users' data. 6 years later, in 2024, NEAR protocol grew in a 8 billion market capitalization. They have millions of transactions every day, and they just announced some big goal on their roadmap is to aim to user-owned AI. So why did we build a NEARCoder? Well, Code LLM are here to help developers coding dApps on the NEAR protocol. And while Web2 technologies are well covered in tutorials and forums, the Web3 is still an Ethan tech with a limited coding support. So it's hard to hire developers in the Web3. And we believe that a powerful Web3 coding assistant to help developers to code apps would be useful in that context. So we came with this protocol of training. It's a 3-step protocol. The first will consist in a continued pre-training of the SOTA 2 by using some general knowledge resources on the NEAR protocol, like blog articles, docs, papers. Then the second step consists in a structure-aware fine-tuning, where we are instructing the model with dApps trees and README files that we will be translating in user prompts. And at the third step, we tried some specialized fine-tuning by inputting the model with AST segments of code files extracted from the examples of NEAR dApps. In terms of datasets, well, it all started by scraping 3,414 GitHub repositories after cleaning. And then from those examples of apps built on the NEAR protocol, we've been able to extract more resource. First, like 3,414 dApp trees for the structure-aware fine-tuning. We also extracted 23,000 dApps README file that has been translated into user prompts and description for the outputs of the model. And we also extracted more than 100,000 NEAR dApps code files that will be segmented in abstract syntax trees paradigm. And those has been complemented by 1,154 docs files on the general knowledge on the NEAR protocol. So all this data I'm speaking about, they are available in datasets. They are open sourced on the Hugging Face platform, as well as our models and intermediary models. So anyone can take over and start to improve this process. Our training data have been prepared and published, in 3 different data sets. The pre-training NEAR, the NEAR dApps prompts, and the IST code NEAR are the name of those 3 data sets. Yeah.
Yes, so as Julian already said, we had 3 steps to get to our final model. And the first step was the continued pre-training of the SOTA. So we used all those official documents just to train the model on general information about the NEAR protocol. And we used a supervised fine-tuning approach and hardware acceleration with NVIDIA A10. And the result was the new model, the NEAR pre-trained SOTA 2. Then in the second Yes, in the second step, we did the structure-aware fine-tuning. So we basically believe that the first challenge in building an app is to get the proper structure for the project. And near depths are often different from normal apps in the structure. As you can see on the right, there's an example tree structure. So we used from our initial data set all the repositories that we had, the README files and the trees from it. And when you go to the next slide. Yes, so based on the README files and the trees, our first challenge was to create a new data set for direct preference optimization. And that means we need not only the labels and the user prompt, but also rejected texts. So we first had to create the user prompts. So we extracted the key data from, the key information from all the README files and the repositories using the OpenAI API with GPT-4 engine. And then we asked the engine to create prompts based on that summarized files, basically. And we therefore transformed the details into user prompts. In the next step, we then plugged in those user prompts into, no, can you go back, please? Sorry, into our pre-trained models that we have from the first step and asked the pre-trained models to create new trees. And then we basically had two trees for each repository, the original one and the one that we created. And we assume that the one we created from the pre-trained model is less accurate than the original one. So we use that one as the rejected text and the original one as the accepted text for the model training with the direct prefer optimization. And then as a result, we get a new model number 2, the NEAR-tuned StarCoder 2. And in the next slide, you can see, oh, you skipped one slide. Okay, it's
which
fine.
one? Okay.
It's not in there. It's fine. In the third step, then we did the specialized fine-tuning. So we basically repeated step 2 with supervised fine-tuning, but this time we tuned the model not only with the general information, but with actual code examples. So we used more than 100,000 code files in JavaScript, Rust, and TypeScript. And again, we used the same hardware. And with that model, we produced our final model, the NEARCoder.
Yes. So then for the evaluation task, as mentioned by Annie already, so there is kind of a problem because on the human evaluation scheme, there are not so much like kind of developed coders so that we can test everything that is kind of generated by our NEARCoder. Nevertheless, it's kind of the idea we also want to emphasize and deepen, or maybe in the next weeks. So we see some improvements there. So there is also that we try to generate like near questions, so to see whether the model has learned something actually by our input. And then on the app side, so is it actually possible to generate kind of the trees, or let's say the comments we have feed it inside it, and then as a major goal, maybe then for building some simple app structure like something like a calendar or maybe like the stake game, so which we would consider as kind of as a benchmark. If this would kind of achieve this, would be very high accuracy on, or maybe on the functionality of the usage of a NEARCoder large language model. So again, the metrics, there are, as you know, maybe in these natural language processes, screen like the blue score, the rogue score. Nevertheless, they're maybe not kind of the best scores or metrics we might use, because usually they are used for translation tasks. If you go from English to French, we do not have like a specific translation task here per se, but also maybe for the rogue score, you can then, let's say, compare maybe something like a summary score to use like larger engrams, and then to compare your structured output maybe with the input, what Annie mentioned, to say your kind of your wrong classified or maybe less accurate tree structures which might be generated, to have, let's say, just a metric which you can then evaluate actually your model on. And then as an ultimate step to see whether the app which is going to generate, whether it allows like full functionality, usability, and the code quality. So we calculate quite lots of these measures. Usually it's not so good to show like large tables on the screen, lots of images or lots of numbers here. So we try to reduce it a little bit, maybe on 2 or 3 graphs. So you see on the left kind of the average score. So we don't, let's say, focus here on the real name, but just we have to compare the numbers. So the kind of on the human eval task, and then on the NEAR questions to ask like specific questions on the NEAR protocol, and then is it able to in the third column to generate kind of tree structures, and then in the end some kind of basic app development. And so the blue line, like the StarCoder 2, so it has kind of no previous knowledge about the NEARCoder protocol, so it would like follow this roughly the yellow curve. Maybe here it's a little bit down, as you can see. So we were kind of able, even with the in the like kind of first step, to have some kind of feeded some useful information about the NEAR protocol into our model with some slight improvement. And then in the next step, so the structured actually data set or structured protocol is kind of pretty much better. As you can see, there's a very large gap here. So there was something important learned or fine-tuned, and nevertheless then it loses maybe a little bit accuracy in the third step or for the app development part. But this is maybe something we could hopefully improve maybe on the next run. So we have some multiple ideas in our on our roadmap so that we can potentially then improve our outputs. And actually, maybe to conclude, or maybe also to show some in the future, so to say, so some vision for the future. So we were kind of able, so it's still kind of this coding challenge and trying to improve these NEAR knowledge actually through the language model. Maybe there will be like different coding architectures, so different coding large language models, which might be more useful maybe compared to StarCoder 2 and maybe upcoming versions to this. But again, like hardware is then an issue to fine-tune this to make it feasible and runnable and accessible, and also maybe that we can pay it or afford it. Another thing, so we also think that maybe the model size is an issue again. So we expect if you would go for a StarCoder 15B model, it should perform definitely better, because then we have maybe also like more weights. And as you maybe remember one of the slides, that the structures may be kind of complicated, maybe it's lots of steps which are important, that you get the JSON files and then the Rust files somewhere. So this is maybe kind of the challenge for the model, why it's not maybe that good performing on a, let's say, on a 3B level. And I think we wanted to keep it short, our presentation. So I think we are then finished, and we thank you for your attention.
Do we have any questions?
Yes, I do. I do have two questions. So first of all, did the data scraping on your own?
Yeah, I did the data scraping. I did it. It took a month. So if you wonder how much it takes, it took a month for a computer that was almost never shut down.
Crazy. That's very impressive. And how much did it take to fine-tune it all in all with the GPU, specified CPU, and how much did you pay for it?
That was pretty cheap and fast compared to, I think, yeah, we didn't work on the same, so maybe Annie can say later what she did. On my side, the training was done using auto-train from Hugging Face, and I think I sent them a credit of 10 euros when I started, and now the credit is burned, but I mean, I finished what I had to do, so.
I think I paid another 40 or 50 quid for the OpenAI license, and then for Colab for training resources to actually create the labels for the structured pre-training. Mm-hmm. And Christian also,
we also
had
tried
the evaluation.
Right, so also to train it maybe on the Colab architecture, it didn't perform very actually well. We had in the end it was crashing quite lots of times, so we had also like tried to replace maybe the StarCoder architecture with a kind of distilled version of the GPT-2 thing. So this kind of worked, but as you go for larger architectures, it didn't perform quite well. So then Julian could run it on the Hugging Face, let's say, interface. So this was kind of feasible, but yeah. It's again a hardware issue, somebody should be aware of. So I think if you would, I think for your model or something which Stefan presented in the beginning. So if you would go for a 70B model or even larger, then it's again a little bit a challenge.
Yeah, very impressive.
Thank you. Do we have one other question? No. Okay.
Okay, yeah, maybe I have a comment as well. So I think you were kind of really successful in creating the trees. That looks very promising, and I think that's something you can really build on. Considering the generation of the actual code, I would have also expected that you actually need to train a separate model, that you cannot do it with the same model, because it's such a different task. The one is creating trees and the other one is creating code. And you could even think maybe that probably in your tree structure, the segments will be very different considering their task. The one is maybe creating a user interface. The next one is creating the queries for the database and stuff like that. So maybe even for those tasks, you could try to train specialized models. I don't know, maybe not, because they have to interact in a way as well. And then you have to provide the database structure in a structured form to the model that creates the user interface or stuff like that. But I think thinking how you would do it as a human being again, you start with the structure of the project and now you start implementing the project. How would you start? Maybe you start creating the database structure as the next step, thinking about how the tables would look like. So maybe that would be your next model to create and train. And I think step by step like that. And the easier you break down the task and the more closed it is, like you provide like just the information it needs, and the task is as small as possible, but you are able to provide all the information you need to do this task. For example, to create the database table structure. And then it's the easier it will be for the model, and the better it will be, I think. So I think particularly because in general it's a very complex problem, and the main task is how you can split it into small feasible parts, and that's what you're doing as a human being, and that's what you have to kind of not teach the model, but allow the model to do, and then organize the steps in that way.
Yeah, that's interesting.
The idea.
Maybe those different models you're speaking about could be like merged in some mixture of experts. That will be a way to have different experts that run at the same time. I'm also seeking that the AST segmentation instructs should maybe go before step first, because somewhat we are creating structure at step 2 and we are crashing the structure, we are breaking the structures at step 1. So at step 3, maybe this let's say code files instruction should go in the continued pre-training, just to make it more tied to needs.
Or you have to do it in an iterative way. If you are anxious that you have to break kind of the structure of the tree in step 3, that you actually then go back to step 2 and you provide the model that's generating the trees with some additional information that you gained in step 3, where you noticed, the tree doesn't work like that or something like that, and then you go back. Considering the mixture of expert model, it would maybe be nice to have just one model, but I would think when you know that you have to use a certain type of model for a specific task, then it's better to do it deterministically and train a special model.